got started. Wow. So I share my screen. No, not yet. Before, yeah, you can see now. I think you can see my shared screen.
Yes, I can.
Yes,
Also,
yes.
the slide, okay. So in our web, you have a pack of slides. That is the first pack of slides. Part 1, POSIX Essentials. We will go very fast in addressing all the slides. And I want just to point out which are the more important concepts, just to get as soon as possible to a level of writing programs. Oh, we have also to discuss the exercise last week. We will do when we stop, and I will give you the possibilities of the possibility of writing, of solving a new exercise. First, we will discuss briefly last week exercise. So, POSIX Essentials. Or let me say that is a, just to be correct, this is historical slide. Historical.
Just a thing, Professor, we can see just the file directory, not the presentation.
Okay. I wanted just to know that. Let me.
Yeah, didn't know if you started.
No. I started, but I have to change.
In the directory.
I always forget that I have to change, and to. So you see the slide.
Yes.
You see the slide.
Yes.
Just
now
writing on the slide.
Yes.
And saying that this slide. Well, this is the first pack of slide. This POSIX Essentials. And first, we will talk about files and directories and processes. This is an historical slide, so I think I will make some changes and upload the newer. Historical in the sense that today, all this is POSIX. The last POSIX release, I think, is 2017, and all those levels are included in POSIX. And first, there were 3 levels. A level in the standard library. The upper level was completely POSIX, and an intermediate level with some calls, the library function that were both on both the worlds. Now POSIX is a standard for everything. So any primitive of the C language is at the same time POSIX compliant. I will show you. I will write on also on the slide. So that's a similar slide. So the idea in general is that in user mode, so when you run a program, you call a system call. The system call jumps in the standard library in what is called the wrapper routine, as to say a routine that makes it independent from the operating system, from the release of the operating system, and so on and so forth. So in the appropriate wrapper routine, calls the kernel, goes into kernel mode, issuing the system call. The system call using interrupt activates the service routine. The service routine is the same kind of routine that is activated by any interruption, hardware or internal interruption. And as soon as the service routine goes back, the system call handler talks to the switcher and gives back the results of the system call, and with all effect, for example, opening a file. In that case, you will have an open file after that. So when we talk of system calls, we are always talking about how to run the kernel in kernel mode after or servicing our request in user mode. Some practical information. Headers. There are many header files. You will see and learn the most important header file to compile your exercise and the programs you have to write. How to know which is the header file? Well, as soon as the compiler complies that some definition is missing, you know, and usually the compiler also points out the necessary header file. But in any case, the right answer to the question, which is the header file I'm needing now, is to look at the manual page of the system call. You see, these are the most frequently used, and in the examples you will have many. This is not well necessarily a POSIX standard, but in general, system calls return -1 in case of error, any error. So there is another way of distinguishing between errors. This is very important at professional and automation level of writing system programs. So that's why it seems to be not a theoretical point to learn, but it's very important from a professional point of view. There is a global variable managed by in the header files that is called error number, errno, and errno in any case carries the last error that happened, but you don't have to read directly this variable, and it carries the error in symbolic form. You will see that there is a primitive, a specific primitive to get the error, to write the error, or on the interactive terminal or on the log file. Here are a series of possible errors. Errors have number, an integer number, and a symbolic name. Operation not permitted, no such file of directories, very common, no such process, interrupted system call, input output error, and so on. There are many. Probably you will find in your exercise some of them. For example, broken pipe, when two processes want to communicate each other and you have established a pipe, you will learn how to do that. And the pipe, for some reason, is broken. That means that the channel is interrupted. The main function, the main system call for diagnosis in case of errors, and is absolutely important in unit debugging. So important that I will ask you to use it, and I will evaluate your assignment also on the basis on how much you are treating all kinds of reasonable errors that may happen. The P error, that means print error or error, is really the easiest way to manage the last error that occurred. You pass the print error string, and simply the print error converts the code of the error into an English message. The prefix of the message is the string you passed. For it is important just to make you understand, to make you know where the error occurred from the point of view of code. So usually in that string you put the name of the function, or somehow also the line of the function, or any kind is useful to understand when the program has trapped into an error, where the error was raised. So this is the prefix, and then the kind of error. For example, function line 24, broken pipe. This is a possible message. This is the way of detecting errors for debugging. For example, this is a very simple example. You open a file, we will see exactly the same. Open. If the return is -1, means there is an error, and you print error main, assume that main is the string you are interested in, and this is the printout. Other practical issues: manual page. All documentation for POSIX standard is in a textual form, in a database of manual pages. The command that you can issue with the shell is man, section is optional, and command name. If you do that, you will have some printout like this one, for example. Name, synopsis, the form of the template of the manual page is standard in POSIX. It's complete textual, so no drawings, no images, and so on. And it must have the names to which the manual page refers. The include, so you see here which are the include files necessary, other external data, and so on, and description and manual. Manual sections are several. Usually you just print, the digit man command, or man name of a function of the system call, and you have the answer. In some cases, there is an ambiguity due to the fact that the same name is contained in more than one section. In that case, you must prefix the section. Normally, general commands are all the typical shell commands. Maybe you have seen my long tutorial about the shell, and you have seen a lot of commands. And the usually shell commands and built-in commands are in the document that is in our web now. It's not necessary to study it, of course. It's just a manual, just to use properly all the commands you need to develop your to solve your exercise and to program. Library functions, system calls, and general commands, and a lot of other things. Well, files. Why files? We talk about files. We talk about files, and there is a short list of categories, because a POSIX file is not just a file on the disk. It's an abstract idea, an abstract concept that is an abstract entity, which is the way of transferring data, process to process, process to kernel, kernel to process, process and devices, input output, and also the network. So file is just a sequential channel. We will also get more in details regarding files, the POSIX files. So when you, the first thing you have to do is to open a file. Open a file means that after you have opened the file, your process is able to access the file. And the file returns a file descriptor. Sorry, but this didn't work. Okay, the stylus didn't work anymore. Okay, I can use the mouse. File descriptor. The file descriptor is an integer that identifies the file as soon as it has been opened. Notably, file descriptors are 0, 1, and 2. All file descriptors start from 0, integer number starting from 0, and all your process start with already 3 files opened. You don't have to open them. You cannot open them. They're opened by the kernel. And so when the shell runs your processes inherit those open files. You will see which is the concept of inheritance of files. And this is the way in which the hierarchy of processes communicate each other, because they shared already open file stored in the user area. Standard input is connected to the keyboard. Standard output is connected to the window that you are using now. And standard error is the communication channel in which the P error prints any error. And by default is connected to the same terminal window. So first you have to open, and when you have finished using the file, you must close. In that case, the file descriptor does not exist anymore and is given back to the kernel. This is really important. It's not a way of sparing space. It's a way of making processes communicate each other. You will see the way. So this is a sketch, simple sketch. Open, path name, read, write, and then close. You cannot close standard input, standard output, and standard error. And so this is the correct synopsis of the open as a path name, and a series of flags. Flags are the characteristics of the flag that you are using. You have seen in my shell tutorial the characteristic of the more important are read-only, write-only, read and write, and also capabilities by users, by groups of users, by users different from the owner of the file. Okay, the idea is that opens an existing file, or in case the file does not exist, it creates the file from scratch. So opens or creates, does not destroy anything. Obviously, open returns a value, and the value returned is -1 if there was an error. Most popular error is non-existing file, but in case of open, this cannot occur, because if the file does not exist, it is created. Or maybe you don't have the capabilities of reading and writing on that directory. going on. You still hear me and see me?
Yes, we can hear, and
okay.
We see the slide, the create.
You see the slide as well. Okay. Create is very similar to open, the same syntax. The only difference is that if the file does not exist, if the file does exist, it is completely scratched, is emptied and created from scratch. So it is a dangerous primitive in a sense. Close is very simple because the file descriptor returned by open or create does not exist anymore, is returned to the system. When a process exits, all open files except standard input, standard output, and standard error are closed by an implicit close contained in exiting. But the couple open and read, for example, what is it for? Read as the first argument the file descriptor, so int. It returns a value, so but it works as side effect. So the return of read is not what has been read, but is a control value. It returns the number of bytes that have been read. And so it is the lowest possible level in abstraction in programming, because you see it fills this buffer that is declared void, so it is not important. That has no type, is a typeless buffer, just bytes. If you have to consider some structured data, you have to rebuild the structure. If it was an array, you will find an array, but in any case, you have all data sequentially in the same sequence they were written on a file. So with no type associated. And this is the control. So you do not read indefinitely, but you specify in advance how many bytes you have to read. So it's the byte level transfer. And returns the number of bytes effectively read. After you have called the read, you have to read, you have to check if the return value is the same as n byte. If it is the same, it was successful. If it is -1, error in reading, and you have to print error and check what's happened. If the number is different, it means that you have found the end of file. Usually is lower than the number you have specified. Otherwise, it is an error. The dual primitive is right. So you define a file descriptor and a buffer, a typeless buffer, and you must specify how many. This is a real example, very simple. You can just write and compile and execute. Copy standard input into standard output. You don't need to open standard input and standard output because they are already declared, already open. These are in the header file of stdin standardin.h that you must includes stdin. And you will find it's a symbolic name of the standard input 0, and this is symbolic name of standard output 0, but you may use 0 and 1 as well. And so you see that you have read this buffer size of a chunk long buffer size bytes, and and immediately written. You see here some typical cryptographic C statement in which you read, assign to n, and simultaneously, just after assigning to n, you check the value of n and use as a control value for the while loop. So you loop as soon as you read bytes greater than 0. If you read 0, means end of file, and so on. The correct print error. We skip this. Well, this is just to remind you that any input output in regular file, I mean files on the disk, this not happens when files are, as we will see, for multi-process communication, in networking, and so on. But in case you have a slow peripheral, like a hard disk, there is a mechanism that is a cache. So when you write, what you write is not immediately written on disk. It's written in memory, in a cache memory. And if you read from the cache memory. So everything is logically coherent, but the transferring the cache on the disk to the disk and read from the disk is delayed and carried out sometimes, just to avoid to read and write physically short data. In solid state disk, the cache is very, very huge, because you cannot write just a single byte on disk. So you have to cache a lot of data before writing, in particular. So the most part of work on a solid state disk is in cache, not on the permanent copy in hardware. And so a problem happens. How can I be sure that after I've written, the data is transferred to disk? You cannot, unless you flush the system. Flushing is in all real-time applications and real-time software, automation, and robotics in particular, is absolutely important. Anytime you want the transfer is effectively carried out. For example, when you want to write a log file, you cannot simply write in a log file. You have to flush immediately, because if the system breaks, if you don't flush, probably you will find in the log file not the last message you thought to have written, because it was on the cache. And the simplest way of flushing is the fsync,